Okay, so today's presentation is about label prediction, simultaneous label prediction, and action learning for active object recognition. So the question is, do you remember GERMS? If not, you should. It's an awesome data set. So it's a data set I collected for active object recognition on the robot, on Ruby. So here's a example video of active object recognition. Basically, there's an object inside the robot's gripper and it rotates it. And then as it sees more images, it accumulates evidence and then can perform a better classification. And the task is to rotate it to a position that helps more with the classification. And the latest development that I did, and I talked about it in the Guru previously, is this deep network, which is composed of a pre-trained 7-layer architecture. And then I added another 3 ReLU layers for policy learning. And the goal of those layers is to output an action given an image. So at each point, the robot sees an image and estimates a position, and then outputs an action. And the action is going to change the next view that the robot sees. And then that label and the belief update accumulates all the evidence through different objects. And we show that the accuracy of this network is more than, that's the policy learning network, and the target value is actually fed through that point in the network. And these are the results on the GERMS. And it showed that it's better than random or sequential action selection. So what's new? I asked myself, can I train the network end to end? And that is, the goal is to do better than just using a pre-trained network. So the error back propagates all the way through the network, through that 7-layer architecture. So here's a proposed architecture that I developed. It's 4 convolution layers followed by 2 fully connected layers. And then there are 2 different pathways. The first pathway is the action selection, which is on the top. And it's basically composed of 3 ReLU layers followed by a softmax. And then the bottom pathway is just 1 ReLU followed by softmax. And the goal of that bottom pathway is to predict the label of the image.
So is this from some paper?
This is just a project that I did. It's not published yet.
Is this architecture?
Yes. So there's a common pathway that is common between the 2 goals of the network. There's an action prediction pathway, and then there's a label prediction. And so the label prediction is just for the current image. So there's an image and there's a label, and I can train it. For the action prediction, it is trained by the Q-learning. So the red arrow here shows the places where the target is fed to the network.
So why is the action selection network so much more complex than label prediction?
Basically, my motivation was that I stick with the old network that I had. I had like 3 ReLU layers, and I just said, okay, let's just crop it and put it on top of this network.
Knowing what you're going to say, that you can overtrain, I would say it's probably too complex. Yes. So, and can you say what is there a target coming down in that brown?
Yes.
Or is that combination of previous, is that a self loop or what is that?
Which one?
Is that
Oh no, that's the target. The brown target.
Backwards arrows.
The arrow is just the target value, indicates that where I fed it a target value. So the gradients from the top and the bottom layer are calculated using those target values and then back propagated. So the common pathway receives gradients both from the top and the bottom pathway.
And the Q-learning is in the top.
Yes. So the cost of this, the cost to train this network is composed of the classification cost that comes from the bottom pathway, and then the Q-learning cost that is from the top pathway. And then the Q-learning is just this formula from the Q-learning. I don't want to go into the details, but it was used previously in my work, and it could train the network. So I used Caltech 101 because it's a smaller data set and it could be trained faster. The input is a 64 by 64 region of interest cropped from the image. So it could be from the object, because the Caltech 101 are annotated by the object boundaries. So whenever I pick a region from the image, I know if it's how much of it is on the object and how much of it is on the background. And then the actions are 8 moving by 10, 40, and 60 pixels in 8 different directions. So that would add up to 24 different actions. And here are the results. It actually learns something. I just compared it to the random, and each column represents the number of ROIs that it receives. So in the first ROI, the prediction accuracy is 31 if I randomly pick the ROI from anywhere in the image. That's the top 2 rows. The bottom 2 rows is when I pick the first ROI, whereas most of its area is on the target object. So it contains like more than 90% contains the target object. And you see that from the only single ROI 64 by 64, which is not that big, the accuracy is 57, and the random is just DQL is the proposed method, and the random is just randomly select one hash. It's 1 over 100 categories, 100 categories. As you see, if I increase the number of region of interest, the performance of the random drops in either way. So from now on, the performance of the networks, the selection of the ROI is based entirely on the network. So I don't tell it that it should be on the object or not. The performance of the random drops because it just moves around on the object and it could go on the background. But the DQL actually gets better over time. Somehow it tends to drop at the end, like for the 5th ROI for the bottom row, when it starts from the object, it tends to drop. Here is a graphical representation. I guess it's easier. It's where the initial ROI is from the object. The recognition results are better. And then the top curve is for the training data. I just showed it because it doesn't learn the training data perfectly, like 90% or 95%. It just learns it by like 70%. You see that the curve for the test, which is the dotted lines, drops as it does more processing on the ROIs, and then the DQL increases somehow, and then tends to flatten or drop.
So, wait, on the previous slide, you had that if the initial ROI was on the object,
yes,
it got 57.7% in both cases. It looks like.
Oh no, that's the training. So the top one is the training data, and this is just for the test data.
Oh, okay.
So this is the bottom curve, the lower performance.
Okay.
So here I tried some just heuristics to improve the recognition rate. One problem that I'm having is that it always converges to one action. So among all the 24 actions that I have, it only learns to do one action, and that is to move up in the image. So it always moves up by 10 pixels in the image, or 20 pixels. And that kind of works because its performance is increasing, but it's not perfect. It's not learning very like complex pattern that can move in the image or over the face or over the object.
Why is it using that? Why is it action?
I don't know. I think there's some bias in the data or somehow. I don't know. I don't have like a good explanation for that. But somehow it learns that that's a good action. What I try to alleviate for that.
So, are you saying that it sticks to the same action after 2, 3, 4, and 5?
Yes.
So yeah. So Tomoki's question is, how can it get better when it's not moving its eyes? So it's getting the same picture every time after that?
Yes, so if it starts on the top, then it goes up and it stucks on the same location.
It's
but
like phasing and updating, but you keep getting the same.
Yes.
The same data.
The same
so
data. Yes.
It's like updating with the same data over and over again. And
it basically converges to that one. Yeah. What I tried is that I tried to reward it after n moves, and that n is bigger than 1, but that didn't work. I tried like after 10 moves or 5 moves, I rewarded. Currently, I just rewarded after 1 move, but I tried to do reward.
Aren't you supposed to reward it after it's done?
Yes, so that's what I tried, and it didn't actually help. One idea is that maybe the belief encoding is not a good idea, because I'm not doing like an explicit memory accumulation of evidence. So maybe if I use some memory units, that would help with the reinforcement learning part. And then the action values are done by the softmax, are calculated by the softmax, and that kind of helps with the convergence, but it actually converges finally ultimately to one action. So if I replace that by the linear unit instead of just doing softmax, that might help, but when I tried that, the training becomes like very slow. It doesn't converge. So, and these are the points. These are the things that I tried on the Caltech 101. So I wanted to train this on the GERMS dataset. Here, the objects, the images are completely resized because we have the human annotation of the object in the image. So we crop the object, resize it to 64 by 64, and feed it to the network. And then the action is actually rotating with different magnitudes, inward or outward. So how are the results? The label prediction accuracy on the training data is more than 95%. So it means that it learns the training data. The network learns it. That's fine. It means that the small image, the 64 by 64, is good for training. On the test data, it does very poor. It does less than 10% accuracy. It means that there's a huge overfitting.
What's chance here?
Is 1 over 136 classes.
Yeah, so that you're still doing better than chance?
Yes.
Okay.
So is this a problem with the DeepNet that I had? I tried PCA and pixels, just the 64 by 64 PCA and then classification. It was still less than 10%. So I said maybe PCA is simple enough. Let's try SVM on some feature descriptors, LBP, SIFT, and HOG. Still less than 10%. So no improvement.
This is just trying.
Yeah, it's not deep. It's just feature extraction like class.
You just get one view.
Yeah, just single frame.
How are you dividing the training? It's just a different German.
Different data collection trials. Again, they were collected in different days by different people. Yeah.
So the pictures are slightly different.
Yes. The pose of the object in the arm is different because it was arbitrary.
But are you training on multiple poses from the first day and testing on multiple poses from the second day?
Yes. So what is the problem? Is it a problem of scarce data? Well, I don't think so, because I have 70K training images and 50K test images. I mean,
that's on which data set?
On the GERMS, yes.
Okay.
And that's not bad compared to Caltech 101, which is less than 10K images. So are the train and test images systematically different? Maybe some bias in the images, but I showed that the pre-trained 7-layer deep network does 37% on single frames. So
That's test accuracy.
yes, on the test accuracy. So it means that it could be learned at least to that point. So so after I struggled a lot with the data, with training different models, I said, okay, let's look at the data. And here are 3 images of my of the GERMS dataset. And the thing is that these are from different classes. They look the same, but they're from different classes. And actually, if you note, like, be very specific, there's a tie in the middle. The neuron in the middle is wearing a tie, and then the neuron on the right is wearing a hat. And that's a graduation brain cell, and the other one is the dad brain cell.
Well,
and these are
also in very different portions of the image.
that's that's a bias in the, but they are the same size.
But yeah, but I thought in the original work you did a bounding box.
Yeah, this is the bounding box.
This is the bounding
Yes.
box. So the stuff hanging down on the right-hand side is part of the.
Yeah, that's part of the the
axon.
The axons. Yes.
Okay, but the sort of where it is in the image is very different. I assume you're
On the
doing,
location.
Are you doing pooling?
Yes, I do pulling on the convolution.
Okay.
And then here are 3 images from 3 different classes: cancer, breast cancer, and prostate cancer. And they look entirely the same, except for that the breast cancer has a pink tie, and the prostate cancer has a blue tie and the blue eyes. So
you want the network to learn to turn it to where those things differentiate.
yes. So what's the problem is that we have similar images, mostly similar, and we are asking the network to learn to differentiate between them. And that leads to overfitting. I guess the network somehow learns, so the deep net tries to capture variations in the images. And there are object appearances which are different because there are different classes of objects. There are object pose in the image that are different. So for different objects, we don't have the same exact pose in the object in the image. So they are different because the test data, the training data was collected with different poses. And then there's the background that is changing in each image. So these are the nuisance factors, and if the deep net learns them, it leads to overfitting. So I have 3 suggestions. I hope we can discuss them. 3 suggestions to avoid overfitting on the GERMS. So the first one is to discard the pose variations in the sequence of rotation of objects. The thing is that I have some extra information. When I rotate an object by a small degree, I know how much I rotated it. So I know that if I rotate it by like 5 degrees, the 2 views should be very similar. So maybe these 2 similar views, consecutive similar views, should be very similar in the network presentation. So that's the activation of the network. So the cost here would be the classification cost as before. Here the T is the sequence of images in a track. So I give the object to the robot, it rotates it, and then all the images that it collects is in T. So the cost to train the network is composed of classification individual images, plus the reinforcement learning cost that comes from the other pathway. And then here's a third cost, which is added to the 2 other one, and that's the distance between the code of the images that are adjacent to each other. So if the object is rotated by 5 degrees and I have 2 images, their representation in the network somewhere up top, for example, in the fully connected layers, they should be similar. So I penalize the network by saying that if they are different, I just penalize the network with that cost. So the WJK is the weight that I give to the distance between two consecutive images. And that weight depends on how much they are different, how much the angular distance is between two images. The second approach is to capture the pose variations in a separate pathway, like explicitly train something that learns the pose variations. And this is the proposed network. It has the two pathways from before, but the bottom one is trained to capture the pose variations. And the output is somehow it uses some memory units, and then it outputs, for example, if two consecutive images are like 30 degrees apart, it outputs something that is encoding of that 30 degrees. And then how can this help the learning in the other pathways? Through the cost function. So I have the classification cost from before. I have the reinforcement learning cost again from before. And then I'm training the pose estimation. Because I know the pose of each image, I can train this pathway. And then here is the fourth cost, which tries to make the pose encoding from the identity encoding dissimilar. So I have one layer in the label prediction pathway that is fully connected, and I have one layer in the pose estimation pathway that is fully connected, and they are the same size. And one of them captures the appearance of object, and the other captures the pose of the object. And then some sort of distance between these two representations could be used to make them as far as possible. And that pose identity similarity somehow is the cost that I add in the training of the network. So that double arrow shows where I want to compare the two layers of the network. And then I want to go to the third approach, is that what if we relax the labeling? Instead of forcing the network to learn all these different classes while they are similar, I just give it subcategories of objects. Let's say I reduce the 136 to 50 categories, and then train it. And then after the training is done, I continue with the full set of objects so that it learns some good features, hopefully, because it's not overfitting anymore in the first stage, and then continue with that to train the full set. And then it again has some challenges, like how to define categories and how to continue from the first training to the second training with different number of labels. For example, I used one image with a different label in the first training. I use it with a different label in the second training. And does that cause any problem or trouble in the training?
Well, you start out with the same weights that you have subcategory, right?
Yeah. And these are three approaches that I want to try. I don't know.
This last thing, I was very confused with this one. This was done on internet for a couple of years and stopped caring about it. But there they have a hierarchy of objects.
Yes.
So it's a tree. So like it's an animal, a four-leg animal, you know. But,
Yeah.
so you can probably find some work on that and some like lots of them.
Thanks.
I really like you guys working with trees. It's a natural way. Then, like, it's a natural way to find the subcategories. Like the two examples you had, like the cancer, the brain cells, you obviously go.
Yeah.
The leaves of the tree, and you can build something up.
Yeah.
The other thing that I would suggest as an idea from psychology literature, actually, that I haven't seen that much, which is like overlapping clusters. Like you can partition in a bunch of different ways. So that they would have like blue eyes, not, you know, you could have things that are gray or not, and like these small boundaries, but it, it's obviously what you do like for animals, right? They have 2 legs or 4 legs, but some people have pets, you know, 2 legs, duck, you know, so it's not the same as having to destroy kind of a little more coarse.
Kind of like attribute classification.
Yeah,
Or,
like attributes, exactly.
cool, thanks.
So the typical way to deal with overfitting is to reduce your model size, right? So
Yes.
I think one problem you probably have is that you've got 4 layers trying to decide where to look next. You know, 5, 12, 5, 12, 24, 24. And I think, you know, first of all, I think there should be more shared between the 2 and then less separation.
Yeah.
So, you know, I would try removing some of the layers you have. It seems to me like the belief part should be the one that's doing the image recognition, right? So that one needs to be reasonably deep, I guess, and then the action part less so. So I guess I'd suggest that you're not exploring the architectures enough before you switch over to exploring different cost functions.
Actually, I tried that. I tried a lot of things. I reduced that to like 2 convolution layers followed by just 1 fully connected layers, and that's it.
Yeah.
And then it learns the same thing. Still learns with the same capacity, like let's 6-7% accuracy on the test. So
Yeah. Okay.
I tried like very deep, like 5 layers with 3 fully connected, and then I decreased it. It had just like 2 convolution layers with 1 fully connected. It still didn't work.
I think the other thing is that I don't know how much pooling you're doing, but the difference in those 3 images with the last one being way shifted up suggested to me that you should try and do a little better job with the bounding bounds.
I see.
But, yeah, so I sent you a couple of papers today about this, and what they do is they keep the 2 networks being the same for longer, and then a smaller set of layers to figure out the next location, the next belief. But they also were LSTM networks, so that they were maintaining the memory from the previous time step. I'm not sure how you're updating your beliefs after each step.
The beliefs is updated by naive Bayesian, so it's not actually it's fixed.
Right,
And
the network doesn't know that.
yeah, the network is not involved
So
in that.
instead of using a Bayesian updating,
Yeah.
you use memory in the network to remember what you just thought.
Yeah.
So, anyway.
Not yet. That could be extended like logically if it learns.
That's another thing is this network I sent you, they're choosing an XY location in the image also, which would obviate the need to fix the bounding bounds problem.
Yeah.
Yeah, also, is it possible, or kind of maybe like Jeremy said, but is it possible I don't think that incrementally, as in like, you start to, the key value is just using 1 layer, then you add next layer to or something. That's all.
I haven't tried that. I don't think I've seen any work doing that. So yeah.
Is there anything recent that does that at all?
What? What's the question?
Yeah.
Just the video of like adding layers. Anybody done that recently?
I really didn't hear. What did he say?
The idea of adding layers
Yeah.
incrementally.
Oh, adding layers incrementally. Yeah. Well, it's been done for unsupervised learning. I think it kind of makes sense
Yeah, so
for supervised as well, but I think in this case, you just want to get it to work better than it's working right now.
You just want to
You
get
got
it to train.
57% or something like that, or
Yes,
when you started right on the object, and
that's
that
right.
was test.
Test set, yes.
And that's the best result you've gotten so far, right?
Yes, that is with the pre-trained network. I mean, in the single frame it's 37%, but it adds up to 60 something.
that's what VGG.
Yes, the VGG 7 layer.
So basically VGG is really good.
Yeah, exactly. It is.
But didn't you have one where you trained it and it was, and you started it on the object and it got some margin that, correct?
That was on Caltech, not on the GERMS.
Oh, right.
Yeah, these
Okay.
ones are on the Caltech. Still, the VGG learns categories. Like when I look at the misclassifications, I see like I printed the images and like, for example, all the cancers are labeled together. There's a lot of misclassification between them. So it basically learns is doing categories. Yep. Okay. Yes, we're done.